Hello friends, in our previous discussion we considered a specific form of materials behavior and we arrived at or we derived a toy model for it. So the behavior that we considered was heterogeneous nucleation. So the specific type of heterogeneous nucleation, it deals with a system wherein you have a nuclei. The subsequent growth of the nuclei will be along the boundaries of the existing nuclei. So in this case, we were able to arrive at a relation that the nucleation rate, in this case, when the subsequent nuclei, the subsequent nucleation event, it occurred on the boundaries of the existing nuclei. In such a case, the nucleation rate can be expressed in this manner, where k is the proportionality constant and x is the number of nuclei that is present at a given time t. So this relation we were able to extract by considering such a system, and we were able to solve this expression here, and we were able to derive an expression in order for us to estimate what would be the number of nuclei for a given time t. And this expression yielded us a relation thus. So we were able to arrive at this expression here, this relation here, by considering the nature of the system, and by solving this expression we were able to arrive or derive a relation that will allow us to calculate the number of nuclei in a given system experiencing heterogeneous nucleation for a given time t. Now this k is a proportionality constant. However, this lambda, it has a unique role. We saw it in our previous lecture. The value assumed by this lambda is nothing but the value of the number of nuclei, or the number of nuclei that we observe when t is 0. So this lambda is nothing but the number of nuclei when the t is 0 during or the initial stages of the nucleation, and therefore this we refer to as the initial condition. Now when you express lambda as x naught, considering that it is the number of nuclei at time t equal to 0, then the relation can be rewritten as the number of nuclei at a given time t is x naught, that is the initial condition, e power kt. Now towards the end of the previous discussion, we considered why we happen to observe this e, that is this particular constant, appearing in too many places when we are considering, particularly when we are considering a physical behavior, be it a behavior of a material or be it behavior of a system. We often come across this particular term here. This term we refer to as Euler's constant or Euler's number. There is a specific reason for it why this comes up often. Now one of the specific reasons is the material's behavior that we often deal with might be of this form here. So this form we refer to as the first order linear ordinary differential equation. So first order linear ordinary differential equation. Now when the model involves such linear linear ordinary ODEs, then it is possible that this particular term will be involved. So when you have a linear ODE, then it is possible that we can be sure that at one instant or the other, this particular constant will be involved. Now this is purely from a mathematical perspective. There is also a physical significance for this Euler's number. So why the role played by the Euler's number, it also can be attributed to the physical system, the physical behavior exhibited by a system. So there is a unique feature this Euler's constant or the Euler's number captures, and that's the reason why we observe it in too many places. So what is this physical feature? Now when you consider, we are considering so far in this context we are considering heterogeneous nucleation. Now let us consider the growth of a precipitate. Now when you are describing a growth of the precipitate, you observe that at the initial time step, that is t0, the growth of the precipitate is of the size 1 centimeter cube. Now at time step t1, as we allow the precipitate to grow till it reaches a time step for a given time period, and we measure its size what you observe is the size of the precipitate has increased by, it has doubled, and now it is the size of, and now it assumes the size of 2 centimeter cube. So you have a precipitate at the initial condition of size 1 centimeter cube. You allow it to grow and you measure its size after certain duration. You call that duration, or you call that specific time as time step t1, and at that time step the size of the precipitate has doubled, and what you measure is it's 2 centimeter cube in size. Now this description is rather a discrete description, meaning what we identify here is we are just considering two different discrete time steps, and then we are saying that okay, in the one time step we have a specific size and the size has doubled in the other time step. Meanwhile, what is happening, what is the evolution, or how this has evolved, we don't have any information about it. So we have a discrete information, two discrete information on about two different time steps and the size of the precipitate in these two different time steps. Now what Euler's constant, what it helps us to do is, it helps us to translate such observation into a continuous one. So physical behavior is often continuous in nature. However, when we describe it, for our convenience, we describe it as a discrete set of events. In time step 1, it is like that, 2, it is like that, 3, like that, so on and so forth. But when we want to translate it, particularly in evolution such as this, when we want to translate it and express it in terms of a continuous set of events, then Euler's number is usually helpful to us. Now, how can we express it in terms of, how can we reduce or how can we express it, this evolution of the precipitate as a continuous set of events? Now, one way of going about that would be considering a time step between t0 and t1. So if you consider a time step between t0 and t1, say t half, now we can say that when the precipitate reaches the time t half, it is of the size that is half times greater than its original size. So when the precipitate moves from t0 to t1, in this case it is twice the size of its, or rather it gains, or it is twice the size of its original size. Now in this case we are considering a time step that is between t0 and t1. Now our description is when the precipitate reaches from t0 to t half, it is the half a size of its original size. It increases by half a size of its original size. So here it increases by its own size when you consider from the propagation or its evolution from t0 to t1, it increases by its own size. So initially it was 1 and it increases by its own size, so 1 plus 1, we end up having 2 centimeter cube sized precipitate. Here we have the duration, and therefore what we consider is, now when the precipitate reaches t half, it increases its size by half its original size. So initially it is 1 centimeter cube, so we will get rid of the unit here. So at t0 it is 1 centimeter cube, at t half it is 1 plus half its original size, so it is 1 plus 1 by 2. Now at t1 this would be 1 plus 1 by 2. This is the size assumed by the precipitate at t half, and as it reaches t1, it assumes half of its original size, therefore half 1 plus 1 by 2. Now it is possible for us to take this 1 plus 1 by 2 out, 1 plus 1 by 2 out. When we take 1 plus 1 by 2 out, we end up having another term similar to it. So we are taking this term out and we end up having an expression like this. And ultimately at t1 the size of the particle would be 1 plus 1 by 2 the whole power 2. At t1 the size of the particle would be 1 plus 1 by 2 the whole power 2. So what we have essentially done is, instead of jumping from t0 to t1 directly, we consider a time step in between. So therefore when the precipitate reaches the time step that is t half, it is the half the size of its original size. So it increases by half the size of its original size. Now so we have a duration of t half and we have a duration of t half. So when the precipitate reaches t1, this is the size of the precipitate. Now instead of considering just one intermediate step, it is also possible for us to consider two intermediate steps. Like it is also possible for us to increase the intermediate steps. So again we want to we don't want to jump from one event to another event, we want to make it continuous, and that's the reason why initially we introduced one intermediate step. Now we can introduce two more, or we can introduce additional intermediate steps. So we can consider T1 by 3 and T2 by 3 and ultimately T1. Now in this case, the growth experienced by the precipitate would be, as it reaches T1 by 3, it will be, the size of the precipitate will be 1/3 of its original size, and as it reaches T2 by 3, again the increased size, 1/3 of the increased size will be the new size of the precipitate, and as it reaches T1, it will be the 1/3 of the size assumed by the precipitate in its previous time step. So it will be, when the precipitate reaches here, it will be 1/3 of the size at T0, and the precipitate reaches here, it will be 1/3 of the size the precipitate assumed at T1, and as it reaches here, it will be 1/3 of the size the precipitate assumed at T2 by 3. So what we have essentially done is, we have increased the number of steps. Now instead of considering just 2 events, now we are considering 4 different events, and ultimately when you rather quantify what is the size of the precipitate under such a condition, at when the precipitate reaches T1, it would be of this form, 1 by 1 by 3 the whole power 3. Now we start to observe a pattern. Now when we, instead of progressing slowly, instead of gradually increasing the steps, if I consider, or if I split this the event from T0 to T1 into n different steps. So I'm splitting this event from T0 to T1, this growth event from T0 to T1 into n different steps, and this n tends to infinity, then what I have essentially established is, I have established a continuous event. So initially we have considered T0 initial time step and the final time step T1, and this was just a leap from T0 to T1, and we said that okay, in T0 whatever size of the precipitate, it gets doubled at T1. Now we need to this was rather the information was not convincing to us, so we introduced another time step in between, and this time step is we refer to it as T half. Now in case of T half, the size of the specimen, or the size of the precipitate rather, it assumes half of the size, or it gains half of the size the precipitate assumed in its previous time step, and we were able to introduce one more further information. Now in addition, in the subsequent consideration, we extended this assumption and included 2 additional steps in between T0 and T1, and we were able to show that there is a definite setup, or there is a definite trend that one can perceive when we try to increase the number of time step in between the initial and the final time step. Now when we keep on increasing the steps in between T0 and T1, what essentially we are doing is, we are refining our description of the growth. And now when we section the time step, that is from T0 to T1, into n different steps, and this n tends to infinity, what we have ultimately achieved is, we have then achieved the description of this event in a continuous manner. So we have now achieved a continuous way of describing this event, this precipitate growth event. So when we have such a consideration where we have introduced n different steps between T0 and T1, so initial and final time steps, we have introduced n different steps, and this n tends to infinity, then in that case the expression will be of this form here, where the n tends to infinity, and this is what we refer to as the Euler's number. Euler's number. Now Euler has found out that there is a specific way of quantifying this number. We will be able to estimate this number, what is the actual value of this number in such a case, particularly when you have such an evolution of your precipitate, then that expression would adopt a form such as this: 1 plus 1 by 1 factorial, then we have 1 by 2 factorial, 1 by 3 factorial, and so on and so forth. So what we essentially end up having is, we are, by involving the Euler's number, we have, by considering translating discrete events into continuous one, we were able to arrive at a specific expression, and this specific expression ultimately yields our Euler's number. And how we were able to do so is, instead of considering two discrete time steps, we kept on increasing the number of intermediate time steps to the extent that we introduce n time step, and at the end of the nth time step, so this t1 or the end of the nth time step, it can be t1 or the end of the nth time step, the size of the precipitate can be expressed in this manner. And now this expression is referred to as the Euler's number, and the Euler's number can be estimated by this approximation here. By this series here, we will be able to estimate what is the value of the Euler's number. I believe you are already familiar with that. Now when you have this Euler's number, this is E, and when you express, or when you want to know what is e power x, then all you need to do is substitute the x in place of the numerator 1, and this will be of this form here: factorial x squared by 2 factorial, x cubed by 3 factorial, and so on and so forth ad infinitum. Now if in our case what we essentially have is, in our case we have a system, or we have a model that is of this form here, that is x naught e power kt. Now e power kt, then the t is the variable here. Now it is important for us to note that often when we consider f of x, the x is the independent variable that governs the function f of x. Here in this case, where we are considering the number of nuclei at a given time t, x of t is the independent variable that governs the number of nuclei at a given time t. So number of nuclei is x, the t is the time step. Now in such a case, e power kt would be of this form: 1 plus e power kt by 1 factorial kt the whole square by 2 factorial kt the whole cube by 3 factorial, so on and so forth. So this is the expansion of the exponential term that we see in the model that we have developed. Now this is just to give you an understanding of what the role of the Euler's number in the context of the physical system. Now let us see if we are able to arrive at this expression here, or this model here, that helps us estimate what is the number of nuclei that is present at a given time c using a different approach. Now the approach that we took in our previous discussion can be referred to as the analytical approach. We began with a relation which stated that the number of nuclei at a given time t, the nucleation rate, it depends on the number of nuclei that is present at a given time t. And from that we were able to arrive at this relation that the number of nuclei at a given time t can be expressed as x naught e power kt. Now let us see. So the way we arrived at this expression was, we took, or we rearranged the variables, we did the variable separation, and then we integrated it, and ultimately we were able to arrive at this model here that helps us estimate the number of nuclei at a given time t. Now we will see if there is an alternate approach. So initially in our previous lectures we were able to categorize the approach as analytical and numerical ones, and let us see if there is any approximation approach that will help us reach the same relation here. So starting from here, let us see if there is any numerical approximation approach that helps us reach this model here. Now there is a way of describing any given function. So there is a possibility, there are numerous ways of describing any given function and approximate any given function. So one of the ways of approximating any given function is of this form, which we often refer to as the infinite power series. Infinite power series. So a function can be represented or approximated using an infinite power series. So here let us consider the function x of t. So this function can be represented using the infinite power series as the summation of Cn t power n, where n tends from moves, or it ranges from 0 to infinity. So the function that considers the number of nuclei and how it varies with time can be expressed as the product of a constant and its variable in this specific manner, where the n, it ranges from 0 to infinity. Now it is possible for us to expand this and write it as C0 plus C1t plus C2 t square plus C3 t cube, and so on and so forth. And then one way of replacing this so on and so forth would be the order of t power 4. So what we end up having is this expression here, x of t can be written as C0 plus C1t plus C2 t square C3 t cube, the order of t power 4. Now when you consider the original relation that helped us in deriving, or that directed towards our model, the original relation is of the form the differential of the x of t with respect to t is k power, or the product of k into xt. Now let us include this k to this function here, so k of x of t. So this will be k C0, k C1t, k C2 t square, k C3 t cube, and so on and so forth. This gets represented by this expression here. Now when you consider this C0 in this expression here and also in this expression here, C0 is a constant that this series, or the C0 is a constant that the x assumes when t is equal to 0. So then in that case C0 is nothing but the initial condition x0. So in this expression and also in this expression, C0 is nothing but a constant that the x assumed when t is equal to 0, then it means it's the initial condition. So therefore k x of t can be written as x0, k x0 plus k C1t plus k C2 t square, and so on and such. Now let us try to take the derivative of this term here. So we have the derivative of x of t in the left hand side of your equation. So this is the equation that we have established from, this is the relation that we have established from the physical behavior. So let us consider to arrive at the left hand side of this equation, that is LHS, which is the derivative of x of t with respect to t, and this we will do from this infinite power series. Now when we do that, this expression changes to C1 plus 2 C2t plus 3 C3 square, and you observe a pattern 4 C4 t cube, then it will be order of t4. Now what essentially we have done is we have taken the derivative of this series here. Now the RHS is the right hand side of the expression is this derivative is equal to the product of k and x of t. So we have the product of k and x of t. So this is the RHS. So we have our LHS, we have our RHS. So we already have established our starting point of this problem is the RHS is equal to LHS. And in RHS and the LHS, there is a specific variables that are associated with it. So there are specific variables that describe the RHS and the LHS, and these variables are t square, t cube, and so on and so forth. So both RHS and the LHS, they share a common variable, and that is in the different powers of t. Now since both LHS is equal to RHS, since we have this equality already established, then the corresponding coefficients are equal. So the coefficient pertaining to t are equal, the coefficient pertaining to t0, t power 0 are equal, the coefficient pertaining to t square are equal, because we have already established the starting point of our discussion is this RHS is equal to LHS. This is the starting point of our discussion. So let us try to equate these coefficients. So it means C1 is kx0, then C2, so the C1 is kx0, then this 2C2 is kC1. So we are equating these two, And now it's also possible for us to equate these two. So it means 3C3 is KC2. And finally, it is also possible for us to equate these two. 4C4 is KC3. So we are relating the coefficients of the T values of similar power. So for T0 we equated this. So this pertains to T0, the coefficients of T0. This pertains to coefficient of T1. This pertains to coefficients of T square. This pertains to coefficients of T cube, and so on so forth. We can go on forever, considering that this is an infinite series. Now this expression here, it states C1 is product of K x naught. X naught is the initial condition. Now we can substitute this relation in here, and when we substitute this relation, what we observe is C2 is 1 by 2 of K, and we are replacing C1 with Kx naught, so Kx naught. So when you expand it, you get 1 by 2 of K square x naught. So what essentially we are doing is we are replacing we are trying to express the C2, the coefficient C2 in terms of x naught, and therefore we are substituting C1 as Kx naught, and we end up having the expression C2 is 1 by 2 K square x naught. Now we can substitute the C2 here so that we are able to arrive at an expression for the coefficient C3 in terms of the initial condition x naught. So we can do that. When we do that, what we end up having is C3 is 1 by 3. So we are substituting C2. C2 is nothing but 1 by 2 K square x naught. So this is 1 by 3 K C2. So we have substituted C2, and there is a K here. So what we then end up having is 1 by 3 1 by 2 K cube x naught. So 1 by 3 and 1 by 2 we can write it as 1 by 3 factorial K cube x naught. And now I believe you are able to perceive a pattern. So we have Kx naught 1 by 2, or we can also write it as 1 by 2 factorial K square x naught. Now 1 by 3 factorial K cube x naught. So ultimately then, following this pattern, C4 would be, you can try and substitute the C3 that you identified here in this expression, and what you end up having would be 1 by 4 factorial K power 4 x naught. Now what essentially we have identified is, we have identified the different coefficients that are associated with the expansion of the function that we have originally considered. So we have considered an expansion of the x of t, and we now have identified the unique values of this coefficient that describe the x of t. Now let us try to rewrite this x of t in terms of the coefficients that we have identified. So the x of t is C0, C1t, C2t square, C3t cube, and the order of t power 4. Now the C0 is nothing but the initial condition that we have already arrived. So C0 here is the initial condition. So this is the initial condition which we have arrived. So the C0 is nothing but the x0. C0 is nothing but the x0. Now let us substitute the C1. The C1 is Kx0. Now let's substitute C2. The C2 is 1 by 2 factorial K square x naught, and we will substitute. So pardon me, what we are losing here is we are losing the term t. So it's just not C0, but it's C0 C1t. So we need to have the t here. So the C2, that is the coefficient C2, is 1 by 2 factorial K square x naught t square, and it will be so on. The third term, the third coefficient which we have derived here is 1 by 3 factorial K cube x naught, and this pertains to t cube and order t to the power 4. So all that we have done is we have substituted C0, we have substituted C1, we have substituted C2, and we have substituted C3. And these values we have arrived by relating the coefficients of the different expansions that we have considered. Now ultimately what can be done is we can take the x0 out, the initial condition out. Then what you would end up having is 1 plus kt, 1 by 2 factorial kt square, and 1 by 3 factorial kt cube, and it goes on forever, it goes on forever. Now ultimately this is the expression for x of t, that is number of nuclei for a given time t. Now this we have already seen. So this sort of a series that we have, this series as a unique description associated with it. This is nothing but the Euler's expansion that we have already considered. So this expansion that we have already considered is what we observe when we derive it using the infinite series. So this is nothing but e power kt. So ultimately, by starting from the expression for x of t in terms of the infinite series, we were able to arrive at this expression that we originally arrived at using the analytical technique. So this function that we have started with, this relation that we have started with, it yielded us a model that enabled us to calculate the number of nuclei for a given time t. The same model we were able to arrive at by using this infinite series approximation. So we were able to take a different approach, a different numerical approach to arrive at, instead of taking the classical route of introducing a formula and introducing the integration and already known formula and axioms to it, and arriving at this particular relation here, we were able to do so by considering a different approach, by considering a expansion, a series expansion of the function that is known to us. Now this approach can be adopted to solve any ODEs. So if you have ODEs, the function of the ODEs can be extended in terms of as what we see in form of an infinite series. If it is possible for us to express in terms of the infinite power series, then this approach can be adopted. So essentially what we have done in this approach is we have expanded this series. So the steps that are involved is we have extended this series, we have considered this expansion series in terms of the right hand side and the left hand side of the equation that we have already that we derived from the nature of the system, and we were able to equate the corresponding coefficients, and by equating the corresponding coefficients we were able to express each of these coefficients based on the initial conditions, and once we were able to express each of these coefficients based on the initial condition, ultimately we were able to arrive at an expression that is indicative of that is equal to the expression that we derived using the conventional treatment. Now what we have essentially done is we have used a different route involving power series. Now the same approach can also be, or there is a different way or different series of writing a given expression. So this is one form of writing an expression. So this form is referred to as the power series expansion. There is also another way of approximating a given function, and this way is this my way you would already be familiar with. This is referred to as the Taylor series expansion. So Taylor series, similar to the power series, it also allows us to describe a function by considering its expansion. So it also allows us to approximate a given function. Now when you consider a function like this, x of t, where t is the variable. Now what Taylor series allows us to do is, in case of power series is just continual expansion, but what Taylor series allows us to do, it allows us to approximate a function when you know the derivative of this function at a specific point. So when you know the derivative of the function, say at t is equal to 0, at t 0, so then we can write it as this, we can approximate this function as this. The derivative of this function at the known point, that is t0, and we need to include the t minus 0 plus d square x of t dt square t minus 0 to factorial t cube x of t and dt cube, again all this at the known point, that is t0 t minus 0 the whole cube 3 factorial, and so on and so forth. So what we can do is, the reason I have included this t minus 0 or all this place is to show that in generalized case we will take the difference between the unknown variable and the point wherein we are able to calculate the differential of this function here. So what Taylor series entails is, this Taylor series involves that we know what is the differential of the given function, what is the derivative of the given function at a specific point t, and this specific point t is t0 for in our consideration. So therefore, when you know what is the derivative of a function at t0, then it can be expressed as, so if you know the derivative of the function at t0, this can be expressed as this. All we need so we can just replace this t0 with this term with t, and what you would end up having is x0 and d x of t dt t, or t square by 2 factorial d x of t d square x of t by dt square by 3 factorial t cube by 3 factorial d cube x of t by dt cube, and so on it proceeds. Now again, it is important for us to note that these derivatives are for the known function, that is t0. So when you know what is the derivative of a function at a given point, then using Taylor series it will be able for us, so it is possible for us to approximate this function. Now if you look closely, there is rather one of the characteristic feature associated with this Taylor series expansion. So we saw a power series expansion. In this case of Taylor series expansion, a distinctive feature is we have the t that is increasing, or that is progressively increasing its power. In addition to that, you have this derivative term associated with each of the t terms. In previous case, in power series expansion, these t terms were replaced by coefficient, but here what we essentially have is these t terms are associated with the derivative of the function at a specific point. Now what that means is that only when you have a definite derivative of the function at these specific points, we will be able to estimate these values. Only when your function is differentiable at this specific point, not only first order differentiable but higher order differentiable as well. Only when your function is differentiable, not only the first derivative of it but second and third derivative of it, only when we are able to estimate these higher order derivatives of the function at the specific points, we will be able to rather have the Taylor expansion. When your system becomes non-differentiable, when it has become ill-defined at higher order derivatives, then it becomes rather difficult for us to expand your given function using Taylor series. So let me repeat. In case of power series, the coefficients are, rather the power series is expressed in the form in such a way that there are definite coefficients associated with each of these t terms. So we have different orders of the increasing order of these terms, and as correspondingly we have the different coefficients. However, when you consider the Taylor series, these coefficients are derivative at a specific point, and this order of this derivative progressively increases. Only when your function is differentiable at higher orders, you will be able to estimate these coefficients. Only when your function is differentiable at higher orders, particularly at the point that you know, you will be able to estimate these derivatives. When it is not possible to differentiate your function at this point in the higher order ranges, then we won't be able to have any meaningful terms as this. We won't be able to, supposing if your function is non-differentiable, it's second order non-differentiable, you are not able to differentiate your function and it turns to 0, then all the rest of the term vanishes off. So the Taylor series, when you want to have an actual series, when you want to have an actual Taylor series, it entails that your function is sufficiently smooth so that you are able to get a definite value for the higher order differentiations that act as the coefficients for your t terms. When you don't have sufficiently smooth curve, then what essentially then we would end up having is we would not be able to build a series. Your series will rather be restricted, and therefore the Taylor series expansion cannot be rather adapted. So there is a limitation associated with the Taylor series, that is only when your function is sufficiently smooth so that it can be differentiated in higher orders at a given point, only then you would be able to convincingly use the Taylor series. Now what here we have is rather we have considered a point that is t0, and accordingly we have expanded this Taylor series. So it is also possible for us to assume that your function is smooth at a given point A. So you have a function and this function is smooth at a given point A, that is it is possible for us to estimate this higher order derivatives at the point A. Now in that case the function x of t can be approximated as the function at A in the differentiation of the function at t A, and what we need to consider here is t minus A. And in the same way the second derivative dt square again at A, and what we need to consider here is t minus A square by 2 factorial, and we might be able to observe a pattern A cube at t minus A the whole cube, 3 factorial, and so on and so forth. Now what we have essentially done is we have now arrived at or expressed a generalized Taylor series expansion for this function here, assuming that this function is differentiable at the point t when the variable t assumes a value of A, and since this function is smooth at A, we are able to estimate the first derivative, second order derivative, and also the third order derivative. Now this is the generalized expression for the Taylor series. So what essentially we have seen is, now when you start from this Taylor series and when you follow the same approach that we have adopted for, when you follow the same approach we have adopted for the power series, it is also possible for us to arrive at the similar relation. Now what we essentially have is we have arrived at the factorials, that is the characteristic feature of our exponential of our Euler's number or the Euler's number. Now when you appropriately handle your derivation, it is possible for us to start from the Taylor series and to arrive at the model that we arrived using the conventional and the power series, that is this is equal to e power t. So this we can also derive when we start from the Taylor series as well. Now when you compare the power series to that of the Taylor series, the key difference is we have a definite expression for the coefficients. There you related the coefficients, here we will be derivating the derivative, but still the framework remains the same. So what essentially we have done in this lecture is we have considered two distinct approaches using which we would be able to solve a ODE. So one of the approach we began with the infinite power series. In the other approach we have just introduced the Taylor series, and we have just seen what is the similarity between the Taylor series and the power series, meaning the similarity is associated with how the coefficients are dealt. There we have just the coefficients, here we have a specific meaning to the coefficient, and in case of the Taylor series there is a limitation associated with it, and that there we don't explicitly see the this limitation because there is just a coefficient, but here there is a specific meaning associated with the coefficient. So therefore in Taylor series is rather a specific form of the infinite power series, wherein the Taylor series can be meaningfully adapted. It can be convincingly adapted only when your function is sufficiently smooth at the point wherein you are estimating your different orders of derivative, and using these two we would be able to arrive at this model from the relation that we conjured up from the physical observation. We arrived at a relation from the physical observation, we developed a model using conventional approach, and this conventional approach now can be replaced by a power series approximation or the Taylor series approximation. Now the reason we spent some time in rather revisiting or rather brushing up your understanding of these is because When compared to the analytical treatment of a function or analytical solution of an ODE, these approaches often play a critical role, particularly when we are dealing with a physical system. Often our functions are not as straightforward as we find in a mathematical textbooks. So in those cases, whenever our function is not that known, or whenever we need a different approach for handling our function, these power series, particularly the Taylor series, it plays a vital role. So with this, I would like to end this lecture, and in the subsequent lecture, we will look into ways of solving the PDEs and how the Taylor series would be helpful to us. Not the power series part, we will narrow it down to the Taylor series, how it will be helpful to us. Goodbye.